Morning, everybody. Happy Wednesday. It's Wednesday, right? Today, we're going to go through a couple more topics. We have 3.5, which is on the kinetic molecular theory. Sounds very fancy. And then we have 3.6, which is going to be referencing deviation from the ideal gas law. So the ideal gas law is the PV equals nRT equation that we learned from yesterday. And there's a couple instances where that equation kind of starts to break down or doesn't work as well for us mathematically. So we got the two topics to run through today. I'd also like you to potentially get started on homework topic 2 for Unit 3. We've learned everything already. It's a mixture of problems talking about types of solids, which was topic 3.2. And it's also a mixture of problems using the ideal gas law, which we learned yesterday. So you should literally have everything you need in order to be able to start answering those questions on topic 2. I'm making that due next week, Tuesday, the day before we leave for Thanksgiving break. So please be aware of that. You're more than welcome to get started on that because, again, we have everything we need. So you should be kind of ready to give it a shot. So once this video is over, once you've watched through the rest of this, if you still haven't finished topic 1 from Unit 3, there's a decent little chunk of you that haven't. Please do that first, obviously. For the rest of you, if you are done with topic 1, you're done with this video, work on your Unit 3 topic 2. All right, let's get into it. So the kinetic molecular theory, the objective here for this topic is to explain the relationship between the motion of the particles and the macroscopic properties of gases with the kinetic molecular theory, B, a particulate model, which is like, a picture showing the little particles of the molecules and atoms, and C, a graphical representation, which we'll talk about what that graph means, or there's a specific type of graph we use for this unit. All right, so gas particles are always moving, right? The energy of this motion is what we call kinetic energy. Kinetic energy can be calculated using the equation below. Now, if you've taken physics, this should look very familiar. Also, this is in your formula packet. It is in that same little quadrant we've been hanging out in, okay? But it's near the bottom. So the third one from the bottom, it says Ke, and then it says subscript molecule. I don't have the molecule part on my equation. But that equals 1/2 mv squared. So if you want to calculate the kinetic energy, the energy of motion for something, anything, you use this equation, 1/2 mass times velocity squared. So this is used more in physics, like I say in the paragraph below. For us, we just need it to make comparisons between gases. That's the only context we'll use it in. So kind of like for Coulomb's law, right? We don't actually calculate anything for Coulomb's law. We just use the relationships of it to draw conclusions, right? We've never calculated the attractive force between two particles when we use Coulomb's law, right? We've never actually calculated the lattice energy of an ionic compound, or we've never actually calculated the attraction between a proton and an electron in an atom using Coulomb's law. All we do is we just qualitatively think about, well, how big are the charges and how far apart are the particles? And we use those two factors to make a conclusion, right? Or to draw a conclusion off of what we're given. So with this one, we're doing the same. What we really need to consider when considering kinetic energy for gases is what's the mass, and in turn, what would the velocity be? Okay? It's actually easier than Coulomb's law, in my opinion. So let's look at a couple things using this equation. So one really important thing before we use it, the Kelvin temperature of any chemical sample is proportional to the average kinetic energy of the sample. What that means is that if you have two gases at the same temp, those two gases have the exact same kinetic energy. Okay? This is extremely important when it comes to like analyzing the types of problems I'm going to give you. If two gases are at the exact same temperature, they have the exact same kinetic energy. That really matters. If that doesn't click, or if you don't know that, this whole thing kind of falls apart and it makes it really difficult. So same temp, same kinetic energy. All right. All right. So number one, a balloon of oxygen and a balloon of hydrogen are each at a temperature of 25 degrees Celsius. Which of these has a greater kinetic energy? All right, I hope you're not forgetting what I said, like, 18 seconds ago. But if they're at the same temp, they have the same kinetic energy, right? So where am I here? I don't know if it's going to write. It's not going to write. Don't mind me. I like purple. They're the same. Okay, they're the same. Which of these molecules has a greater mass? All right, now this is different, right? Let's think about it. Oxygen is O2, hydrogen is H2, right? Ooh, nice H. There we go, kind of. Oxygen is very clearly going to be heavier, right? Each oxygen is 16 grams per mole. Each hydrogen is 1.008 grams per mole. This would be a total molar mass of 32, total molar mass of 2.016. Yeah, so the oxygen has a greater mass. Okay, which of these molecules has a greater velocity? Let's go back to our equation. I'm going to run over here, actually. Kinetic energy equals 1/2 mv squared. Kinetic energy is the same for both. The mass is different. Okay? If the kinetic energy is equal for both oxygen and hydrogen, the mass of oxygen is more, what would have to happen to the velocity of the oxygen gas in order for the kinetic energy to still be equal? Well, it'd have to be less, right? So here is the conclusion. Gases with more mass are moving slower when at the same temperature. Gases with less mass, like hydrogen, are moving faster at the same temperature. This is an inverse relationship, right? As the mass goes up, the velocity must go down. As the mass goes down, the velocity must go up in order for kinetic energy to be constant or the same, right? Because again, here's the initial conclusion. The initial conclusion is, what's the kinetic energy? Well, they're at the same temp. They must be the same. Their masses are different. Oxygen is heavier. So oxygen must be going slower. Hydrogen must be going faster. Okay? This is a huge, huge takeaway. And sorry, let me answer my question here. Which of these is greater velocity? That would be hydrogen. Yeah, I'm not very good at writing with this, but that's all right. All right, so that brings us to this. This is called a Maxwell-Boltzmann distribution, named after two dead guys, okay? You know, standard science stuff. And these graphs show up more than once this year, but let me explain what they're trying to show, okay? What we have on our y-axis is the relative number of particles, meaning like, you know, how many particles are there. As these little lines get higher and higher and higher, I've got three different samples on this graph, okay? So as these lines get higher, what that's really meaning is that there are more particles at that specific velocity. Our x-axis here is velocity. So the whole distribution of a sample is the whole bell curve, right? So let's look at the blue one maybe, for example. This blue one represents a gas. In that gas sample, some molecules are moving really slow, underneath 200 meters per second for velocity. A lot of molecules, or a greater percentage of molecules, are moving at 700 meters per second. And then if I go down the bell curve, there's a tiny bit of this distribution that's moving really, really fast, around 1400 meters per second. But the idea here is I have a gas sample, okay? Some things are moving slow, some things are moving really fast, and a whole bunch of them are kind of in the middle. And that's represented by this line getting taller, right? As this graph goes up, more particles are representing that velocity. So it's a distribution, right? And here's the other thing too, and maybe this is a misconception, but when I have a sample of gas at a certain temperature, not all particles have the same velocity or the same energy, okay? When we measure the temperature of something, we're taking like the average kinetic energy of the sample. Meaning, some things are moving faster, some things are moving slower, some things are moving at the speed or at the velocity of our temperature, but there's a distribution, right? We take into account the entire sample of gas and all of the different velocities of all of the different particles. So the peaks of these graphs represent the greatest percentage or the greatest quantity of particles with the middle velocity, you can kind of think of it as. Okay, so we have three different curves: red, green, and blue. The red one, the green one, the blue one, they're all trying to represent the same thing. They're just different examples, right? They all have distributions. Some things moving faster, some things moving slower, a whole bunch of things in the middle moving at that kind of median velocity, you can think of it as. But let's analyze a couple questions here for this. Okay, so assume all three of the curves on this graph represent oxygen. Which curve would be the low temperature, mid temperature, and high temperature? So we have the exact same gas, but we've changed the temperature 3 different times. And now we need to think about, okay, well, what would a temperature change do to our gas, right? And I think this one is fairly obvious. If you crank up the heat, what's going to happen to the velocity of the particles? They're going to go faster, right? That's a direct correlation. So the fastest one here, in other words, the one with the average kinetic energy or the average velocity the highest is going to be the highest temperature. Now, there is a misconception here. This is high. What am I doing? Hold on. Ooh, nice. High temp. Okay. Now, there's a misconception here. The height of the peak doesn't represent the average velocity, right? You'll notice that the red one, there's a lot more particles at the median velocity than there are particles at the median velocity for the blue one. But that's not what that's not the average velocity, right? The average velocity of the red particles is probably somewhere in the range of, I don't know, 300, give or take. The average velocity of the blue particles is somewhere in the range of 700. So that's what we want to look at, right? It's the average. So it's not how many particles are at a certain velocity, it's what is the average velocity of the sample. If the average velocity of the sample is higher, that sample must be at a higher temperature. And that's the blue one. Now, the middle one obviously is you know, the middle one. So this is what I would call my mid-temp. And then the red one here, this is going to be our low temp. And it has absolutely everything to do with the average velocity of these curves. And again, the average velocity is roughly where that peak falls, right? That's kind of the middle of those distributions. All right, same graph, different question. Assume that all 3 curves represent different gases at the same temperature. Okay, so now this is very different. Everything's at the same temp. We just have different chemicals. Okay, so now we need to think back to our kinetic energy equation. Ke equals 1/2 mv squared. Okay, we have the exact same temp, meaning they have the exact same kinetic energy. So what's the difference between these 3 gases? Their mass. They have different masses. Okay, and different mass is going to lead to different velocity. And again, this Maxwell-Boltzmann distribution is showing velocity. These curves represent the average velocity or the distribution of velocities in a sample. So as the mass goes up, the velocity goes down. The curve with the slowest average velocity will be the graph for the molecule with the heaviest molar mass. And I kind of pointed to it, sorry, or well, not sorry, but carbon dioxide has a molar mass of 44.01. Oxygen has a molar mass of 32.00. Hydrogen has a molar mass of 2.016. The one with the most mass is moving the slowest. Mass goes up, velocity goes down. The one with the least mass is moving the fastest. Mass goes down, velocity goes up. It's inverse, right? More mass, slower particles. Less mass, faster particles. So, the red curve, which is representing the slowest average velocity, this is our CO2. The one with the greatest molar mass. The middle one here is oxygen. And the fastest one, or the one with the average velocity being the highest, is hydrogen. Okay, so same exact curve, right? But different question. The first question was, hey, all the same stuff, different temps. Well, as temp goes up, we expect velocity to go up. So the fastest one was the highest temperature. In this one, It's, hey, three different things all at the same temperature. Well, now it comes down to, all right, bigger mass, slower velocity, smaller mass, greater velocity. All right, if I had two balloons, one with helium and one with argon, and poked a hole in each of these, which of these would you expect to deflate faster? Think about it, okay? If you want to pause it, I know you're maybe at your house or you're maybe in school, but pause it. Think about this. All right, same concept, right? Same thing we've been talking about. So argon, if you look it up, and by the way, you should totally have your periodic table and formula sheet nearby every day. Argon has a molar mass of 39.95. Helium has a molar mass of 4. Okay. If I have two balloons right next to each other, spoiler alert, they're probably at the same temperature, right? It's not like I had one in a freezer and one in an oven or something like that. They're at the same temp. So now this totally comes down to mass and velocity. Helium has less mass and a greater velocity. Oy, oy, oy. So helium will totally deflate faster, right? It has to. The particles are moving faster, so they're going to escape the little pinhole much quicker. Okay? So I'll leave it like that. I mean, I didn't quite answer my question, but you understand where I'm going with that, right? It's less mass, greater velocity particles can escape through the pinhole quicker. All right, so that leads us to the next part of this, the next topic, which is called the deviation from ideal gas law. So we're going to explain the relationships among non-ideal behaviors of gas, particles, and volumes. All right, so yesterday we talked about the ideal gas law. It's an equation, PV equals nRT. Very, very nice equation. It's pretty easy mathematically speaking, right? It's just a little bit of algebra. You plug in what you know, you solve for what you don't. Not too bad. Again, there's a couple little areas you have to look out for. We got to make sure that we're using the correct value of the gas law constant, capital R. Make sure it matches the units of the other factors or values that are given. But I mean, really, it's just kind of plugging and chugging, which is maybe easy stuff. I hope that's easy stuff for you guys. But anyway, so the ideal gas law is an equation used to calculate or predict the properties of gases under various conditions. Things like pressure, volume, temperature, number of moles, right? That's what we calculate. So, like I've stated previously, the ideal gas law ignores all intermolecular forces of attraction. This is rarely an issue. Under most conditions, ignoring those forces doesn't really mess with our math. However, there's two spots where this kind of breaks down. And it makes sense why it would break down. So, when gases are very close to condensing into a liquid, the intermolecular forces become much more prevalent, meaning they're more pronounced, right? They're more present, you could say it as. So, under conditions where gases are about to phase change, about to turn into a liquid, the ideal gas law isn't great. But that kind of makes sense because the ideal gas law is 100% ignoring intermolecular forces, right? So if something's about to turn into a liquid, its intermolecular forces are kind of becoming stronger and stronger and stronger to condense it into a different phase. So this kind of makes sense. That's one spot where our ideal gas law doesn't do so great. The other is at high pressures. Under conditions of high pressure, the gas particles can have an effect, the volume can have an effect on the properties that we calculate. Essentially, the atoms and molecules take up space, and under conditions of high pressure, the physical space occupied starts to mess with the math. You can think of it as like you're purposefully forcing particles to get closer together, right? That's what high pressure is. High pressure is decreasing the volume or the space between the molecules or the atoms. And as a result, you're almost forcing those intermolecular forces to become a factor, right? As you lower the space between things, now there's a chance for those attractive forces to be stronger. That's Coulomb's law. Yeah, he's still around. He's never going away. Coulomb's law, again, smaller distance, stronger forces. Okay? So the high pressure messes with the ideal gas law, and conditions where your gas is just about to condense into a liquid mess with the ideal gas law. Under both circumstances, it's really a matter of the intermolecular forces becoming more prevalent or stronger, right? And that's not a good thing for the ideal gas law, because the ideal gas law is ignoring them completely. All right, so in conclusion, the ideal gas law is extremely useful for most gases under most conditions. However, when gases are close to condensing or under high pressure, the usefulness of this equation starts to drop. And essentially the intermolecular forces start to matter way, way, way more. And that's going to mess with our math. All right, so we've got a couple problems here. We'll call it a day after we're done with these problems. And again, please work on homework topic 2 when we're all done. Okay, so a sample of sulfur hexafluoride and helium are used for a demonstration in chemistry class. When the teacher breathes in the sulfur hexafluoride, the pitch of their voice gets lower. When the teacher breathes in the helium, the pitch of their voice gets higher. Why? Okay, why is this occurring? Again, please think about it, pause it, jot something down before I start yapping. I think that's a good thing. That's how you learn. At the very least, think about it, right? Like walk through what your answer is in your head. So please pause it. All right, so sulfur hexafluoride. Oh, there we go. Okay, it has a greater mass. I keep accidentally hitting that. Which means it has a slower velocity, right? So when you breathe it in, the velocity of the sulfur hexafluoride particles are slower than air. So as a result, as those particles pass through your vocal cords, if someone were to try to talk, they're moving slower, and the pitch of your voice gets deeper and lower. For helium, it's the exact opposite, right? Less mass, and therefore greater velocity or faster velocity, right? And you've probably all done this, right? At a birthday party or something. You breathe in helium, you talk, and now those particles moving past your vocal cords have a greater velocity than air. And as a result, the pitch of your voice gets really, really high. So, sulfur hexafluoride, big mass, slow velocity. That's the whole kinetic energy relationship, right? Big mass, slow velocity, your voice goes down. Helium, tiny mass, fast velocity, your voice goes up. The pitch of the voice gets higher. Number 2. A sample of methane and ammonia are collected in a lab. Using the ideal gas law, students predict what the pressure is inside of the containers for these two gases. When the real pressures are revealed, meaning like the right answers are revealed, the prediction for methane is closer to the actual value than the prediction for ammonia. Why? All right? This one's much more complicated, much more tricky. You've got something to think about here. We've got two gases, CH4 and H3. We do the ideal gas law math for both, and then we compare it to the real value of pressure. What the students find out is that their prediction or their calculation for methane is better than their prediction for ammonia. Why? Okay, pause it, please. Try this, think about it. But why would that be better? All right, so I hope you've thought about it. I hope. But this really comes down to the whole nature of the ideal gas law. The ideal gas law works really good for gases with little to no intermolecular forces. And it doesn't work as well for gases with intermolecular forces. So let's look at our structures. We have CH4. Come on, there we go. What a beautiful Lewis diagram. I hope I at least make you laugh sometimes with my struggles. That's not too bad. That's okay. All right, so we have these two structures, right? Methane is tetrahedral, it's symmetrical, it's nonpolar, it's got nothing but London dispersion forces. Ammonia is a trigonal pyramid, and it has hydrogen bonding. The intermolecular forces between the methane molecules isn't the best. It's very weak, just London dispersion. The intermolecular forces between the ammonia molecules, that's a little stronger. It's actually a gas, right? But it's a gas that's very close to condensing at room temperature. And as a result, when we do the ideal gas law calculations on either of these two gases, and we use the real value of pressure that we see in the lab, you would notice that the ideal gas law is not working nearly as well for the ammonia as it is for the methane. It has everything to do with the fact that these intermolecular forces are stronger, okay? So this is nothing but London dispersion. This has hydrogen bonding, okay? And that's why the prediction for methane is better. The prediction for ammonia is worse. It has everything to do with the attractive forces between these molecules. So here's the thing to remember, right? The ideal gas law is all about intermolecular forces. When we do that math, when we use PV equals nRT, we're ignoring intermolecular forces. So it works just fine if you're picking gases that have weak intermolecular forces. But it's not the best when you're picking gases with semi-strong intermolecular forces, like ammonia. Ammonia gas, the ideal gas law would not be great at making real-life predictions because of those intermolecular forces being stronger. Okay? All right. So, which of the following gases would the ideal gas law work the best for? Explain your choices. Same kind of concept that I have here in number 3. Same thing. It's, hey, here's 4 different gases. We're using the ideal gas law for all of them. Which one would it work the best for? AKA, which of these gases is the most ideal? What I mean by that is, which of these gases has the weakest intermolecular forces? Okay? Things with decently strong intermolecular forces, the ideal gas law doesn't work as well for. Things with really weak intermolecular forces, the ideal gas law works very well for. So let's analyze these structures. Again, pause the video. Please don't let me just give you answers. You're not going to learn a darn thing. You really won't. I know you're thinking, oh, I'm kind of tired, I'm kind of lazy, but I don't care. Pause the darn video. Think about it for at least a little bit. You've got to try this by yourself. Me just spewing answers at you does nothing. Okay? So pause it. Okay, SO2. We've done this a million times. I feel like this one's been coming back around quite often. And it looks like that. Okay, the types of intermolecular force here that we have are dipole, dipole. HBr, very easy structure. And by the way, I didn't put the lone pairs around my oxygens. Like total now. There we go. Ooh, that's not good. Oh. That's a B. I don't know if that's better or worse. Whatever. All right. HBr. This has also dipole, dipole. pH3. This is the exact same structure as ammonia, just with a phosphorus in the middle instead of a nitrogen. This has dipole, dipole. N2. Ooh. Oops. There we go. N2. Looks like this. What type of intermolecular forces does this one have? LDF. Nothing but London dispersion forces. That's your guy. So, again, right? The whole ideal gas law situation, the whole ideal gas law concept, what are we looking for? We're looking for gases with very weak intermolecular forces. Wimpy ones. Almost non-existent ones. When we get dipole-dipole, when we get hydrogen bonding, these are stronger types of intermolecular forces. Meaning the ideal gas law isn't as great for them. Works much better for things with weak intermolecular forces. The nitrogen in this example has the weakest of the set, right? The nitrogen's intermolecular forces have the absolute weakest compared to the other 3. All right, last one, and then I'll leave you alone. And again, please spend the rest of your time either A, finishing topic 1 because you didn't finish it yesterday like you were supposed to, or B, working on topic 2, which is due next week. And again, you've learned everything you need for topic 2, just a matter of getting started on it and chipping away at it. All right, so under which set of conditions would we expect a sample of a gas to behave the most ideal? Again, what does that word mean? What is ideal trying to imply? Okay, ideal is trying to say, right, this equals no intermolecular force. That's what ideal means. Okay, so the closer we are to no intermolecular force, the more ideal it is. So let's think about it. We've got two factors here in this little chart. I've got temperatures, I've got pressures. Okay, would a gas be more ideal at high temperatures or low temperatures? Think about that. Would a gas be more ideal at high temperatures or low temperatures? Well, at low temperatures, those particles are moving slower. And if they're moving slower, there's a good chance their intermolecular forces can start to kind of stick them together and we can start to condense that gas. At high temperatures, they're moving faster. They're going crazy. And they're whizzing right by each other, okay? And they have so much kinetic energy that the chances of those intermolecular forces sticking is much, much lower. So I would say that gases are more ideal at high temperatures because the intermolecular forces just aren't able to kind of stick, so to speak, right? They're moving faster. Pressure, let's think about pressure. We have the other side of this chart. Would gases be more ideal at high pressure or at low pressure? Okay, now, the best way to think about pressure is to consider volume, all right? So if these all had the same number of moles, the same number of particles, a higher pressure would be a smaller volume. A lower pressure would be a bigger volume. So would we expect the intermolecular forces to be stronger when there's less space, or would we expect the intermolecular forces to be stronger when there's more space? Well, I would totally expect that if you make and force those atoms or molecules to get closer together, you're going to get stronger intermolecular force, meaning higher pressure. At lower pressures, now there's extra space in there, and the molecules are further apart, which is a good thing when it comes to intermolecular force, right? That lowers the intermolecular force the further they are apart. So I think what we're looking for here is a high temp with a low pressure. Higher temperature, things are moving faster, less intermolecular forces. Low pressure, there's extra space, lower intermolecular forces. And the fourth option is absolutely our option. Okay, that is the correct answer. Under those conditions, we would have a gas that is closest to being ideal. And again, what that means is closest to having no intermolecular forces of attraction. All right, I'm all done. This covers 3.5 and 3.6. Please, again, work on your homework. If you need any help, let me know. I'll be around. Yeah, and we will catch you guys tomorrow. See you later.